Welcome back to QHSE Talks, your practical guide for the ASP and CSP certification exams. The ASP, or Associate Safety Professional, and CSP, or Certified Safety Professional, are rigorous credentials testing the core knowledge needed to manage risk in complex industrial environments. To succeed on these exams and in the field, you must master one essential tool: statistics. Look closely at almost any active factory floor. You are watching raw workplace data in its physical form. Every day generates countless labor hours, mountains of safety audits, and scattered, disconnected incident reports.
For decades, occupational safety operated in the aftermath of these hazards. Organizations counted the injuries only after the workforce had already suffered harm, relying on lagging indicators to tell them what went wrong. Modern safety management requires a strict mathematical approach. For practitioners preparing for ASP and CSP certification, the discipline demands moving from reactive incident response to proactive risk prevention, grounded in data analysis. Statistics provide this capability. These mathematical models serve as practical decision-making tools that take raw, disorganized safety data and convert it into actionable insights, predicting potential hazards before an accident physically occurs. The analytical sequence begins by gathering base operational data. Professionals use that raw information to forecast risks, measure the exact efficacy of specific safety interventions, and engineer mechanical systems for consistent reliability. Mastering these statistical concepts equips practitioners with objective facts. It allows them to quantitatively justify the cost of necessary safety improvements and communicate effectively with corporate management. In this context, statistics are entirely practical. They are the primary tools used to systematically engineer a safer, more resilient workplace. The first analytical layer is descriptive statistics. This branch of mathematics summarizes large sets of raw workplace measurements, like air contaminant concentrations or daily safety audit scores, and organizes them into a digestible format. This chart shows 5 individual noise exposure measurements taken from a factory floor: 88, 90, 92, 87, and 93 decibels. By adding these values together and dividing by 5, we calculate the mean, establishing a typical baseline exposure average of 90 decibels. The mean is highly sensitive to extreme outliers. If we plot lost workdays from 5 separate incidents, a single catastrophic event resulting in 50 lost days severely skews the mathematical average. To correct for this, we use the median, the precise middle value when the data is arranged in order. Here, the median provides a much more stable representation of 3 days. To identify the most common type of incident, professionals calculate the mode. If categorical data shows recurring slip and falls outnumbering equipment injuries, the mode isolates exactly which physical hazard requires the most immediate attention. Central tendency only identifies the baseline. We must also measure the spread of the data using variance and standard deviation, which track exactly how widely individual data points deviate from that central mean. If our average noise exposure is 90 decibels with a standard deviation of just 1 decibel, the environment is highly consistent. If the standard deviation jumps to 7 decibels, the exposure levels are varying wildly across the shift, proving that the current administrative controls are inadequate. Central tendency establishes the baseline hazard, while variance and standard deviation verify whether your controls are consistently keeping that hazard in check. Moving beyond historical records requires probability, estimating the mathematical likelihood of a future hazardous event. This relies on counting principles, like permutations, used when the sequence of events matters, and combinations, applied when the order of selection is irrelevant. This graph represents the normal distribution, a symmetrical bell-shaped curve that governs most industrial hygiene sampling and biological exposure monitoring. Its defining property is that the mean, median, and mode align perfectly at the exact center of the curve. By converting this into a standard normal distribution, the parameters are simplified. The population mean is set to exactly 0, and the standard deviation is set to 1. This standardized format lets us calculate a z-score, a metric measuring how far a specific value sits from the mean. If a facility has an average chemical exposure of 50 parts per million and an observed exposure of 70 parts per million with a standard deviation of 10, the resulting z-score is exactly 2. That specific z-score proves the observed exposure is 2 full standard deviations above the facility average. This mathematical spike confirms an excessive exposure risk demanding immediate engineering intervention. Applying these statistical distributions allows professionals to track process variability and predict when a safe limit will be breached long before any worker develops an illness. Probability transforms a single isolated measurement into a reliable mathematical prediction of system-wide risk. When a company invests in new machine guards, injury rates might drop the following month. The immediate operational question is whether those new guards actually caused the reduction, or if the numbers fluctuated by random chance. To answer this, practitioners use inferential statistics. This analytical toolkit determines whether the data from a safety improvement is statistically significant enough to prove a real-world effect. The specific test depends on the data type. A t-test compares the means between two distinct datasets, like average noise levels before and after installing sound insulation.
A chi-square test evaluates categorical data, comparing observed accident types against expected industry averages. The definitive metric in hypothesis testing is the p-value. It measures the probability that the observed results occurred purely by chance. The standard decision rule is absolute. If the p-value is less than 0.05, you reject the null hypothesis, mathematically confirming the intervention worked. We also use correlation to measure relationships between two variables. This scatterplot maps training hours against injury rates. The resulting correlation coefficient, which ranges from -1 to +1, shows a strong negative correlation. As training increases, injuries strictly decrease. By squaring that correlation coefficient, we find the coefficient of determination. If our correlation is 0.80, squaring it yields 0.64. This proves that exactly 64% of the variation in injury reduction is directly explained by the increase in training hours. Inferential statistics strip away coincidence. They provide the empirical proof required to validate capital investments in safety programs and secure management buy-in. Probability must also be applied to the physical performance of mechanical hardware, like emergency shutdown valves and automated fire protection systems. This is reliability engineering, a discipline focused on evaluating whether a designated safety instrumented system will function consistently during a critical failure event. The baseline equation for any physical component is straightforward. Its probability of failure is always equal to 1 minus its proven reliability. This diagram illustrates a series reliability system. In this architecture, all components must function for the system to succeed. If a single component fails, the entire sequence collapses. Because total reliability in a series is calculated by multiplying the fraction of reliability for each individual component, the overall system is mathematically guaranteed to be less reliable than its weakest link. To solve this, engineers design parallel systems. By introducing physical redundancy, a parallel structure ensures that if one component fails, the operational flow simply bypasses the broken unit and travels through the surviving pathways. Parallel architecture drastically increases the overall reliability of the system, guaranteeing that isolated mechanical faults do not compromise the facility. Safety engineering leverages probability to structure these physical defenses. It creates networks of hardware where total mechanical failure is mathematically neutralized. The micro-level data of z-scores, standard deviations, and component reliability ultimately aggregates upward. Organizations require a method to measure and compare this total safety performance at a macro level. This dashboard illustrates the universal baseline for occupational safety and health administration metrics, the 200,000-hour standard. This number standardizes corporate data by representing exactly 100 full-time employees working 40 hours a week for 50 weeks a year. Using this baseline, professionals calculate the total case incident rate, or TCIR. By dividing the total number of recordable injuries by the total hours worked, then multiplying by 200,000, organizations evaluate their overall injury frequency per 100 workers. For a more focused analysis, the DART rate isolates only severe incidents. DART stands for days away, restricted, or transferred, and it strictly measures the rate of injuries serious enough to pull a worker off their normal duties. To evaluate the exact seriousness of those incidents, the severity rate calculation weighs the data by factoring in the total number of lost workdays, showing exactly how much operational time is bleeding out due to poor hazard controls.
These standardized metrics take individual human accidents and convert them into a universal ledger. This allows executives and federal regulators to objectively judge corporate safety performance across entirely different industries. That data feeds directly into a strict federal regulatory framework. Under OSHA record-keeping rules, organizations are legally mandated to log recordable injuries on OSHA Form 300 within exactly 7 calendar days of learning about the incident. Severe events trigger rapid response reporting timelines. A hospitalization, amputation, or loss of an eye must be reported to federal regulators within 24 hours. Any workplace fatality must be reported within 8 hours. All OSHA logs must be maintained for a strict 5-year retention period. Furthermore, incidents involving sensitive matters, such as sexual assault, HIV exposure, or mental illness, must be classified as privacy cases to protect the individuals involved. Ultimately, these compliance logs and incident rates are lagging indicators. They are the final readouts of the mathematical models and physical control systems built on the factory floor. Mastering descriptive and inferential statistics gives the modern practitioner the power to map those outcomes in advance. It allows you to predict hazards, prove the success of your interventions, and engineer mechanical failsafes. In the hands of a capable professional, statistics cease to be abstract numbers. They are the instruments for proactive risk prevention and decisive safety leadership. Thank you for learning with QHSE Talks. If this content helped you prepare for the ASP or CSP certification, please support the channel by liking the video, share it with fellow safety professionals, and subscribe for more ongoing safety knowledge. Together, we build safer workplaces. QHSE Talks, your partner in professional safety development.